In an electrical system, effective grounding ensures a safe working environment as well as proper equipment performance. This is why electric utilities attempt to provide adequate grounding of the electric distribution system so consumers can enjoy the benefits of electric power and safety. Power utilities strive to produce and deliver high-quality, non-fluctuating electrical energy. Good electrical grounding of transmission and distribution systems contributes directly to the quality of the energy being supplied. Grounding of buildings and other structures is done for a variety of reasons. Radio and telecommunication towers are grounded for optimal transmission efficiency. They're also grounded for protection against lightning strikes. Electric equipment mounted on utility poles is also susceptible to lightning, which is why poles that carry electrical equipment should have particular attention paid to the efficiency of their grounding conductors and electrodes. This video is an introduction to grounding systems. Our goal is to provide you with a good basic understanding of why grounding is important, the environmental factors to consider when designing a grounding system, and the testing required to ensure your grounding system is properly installed and performing to specifications. In this video, a ground is defined as a conducting connection by which an electrical circuit or equipment is connected to earth. This connection is used to establish and maintain as closely as possible the potential of the earth on the circuit or equipment connected to it. This connection to the earth provides a low impedance path for electric currents to travel under fault conditions. For example, most people know that the third pin on the line cord of an electric appliance is the ground connection. When a piece of electrical equipment is plugged into a wall receptacle, the ground terminal connects all exposed metal surfaces of the equipment to a common connection, called the equipment ground, in the building's electric service panel. From this point, the ground connection typically exits the building and is connected to the system ground at the building service entrance. The system ground can be a simple metal rod driven into the ground as shown here, a grid consisting of multiple electrodes, or another type of grounding system. Many electrical faults that occur are caused by nature, while others are man-made, but most occur due to corrosion and general degradation of equipment over time. When these disruptions of normal electrical operation do occur, it's very important for the grounding system to operate efficiently. For this to be possible, the grounding circuit must have a low-resistance connection to the surrounding earth. And a grounding system will only perform properly if it is designed and installed with local soil conditions taken into consideration. So to evaluate the anticipated efficiency of a grounding system, we need to understand local soil resistivity. Soil resistivity measurements are useful for many reasons. For example, data from soil analysis is used to make geological surveys, as an aid in identifying ore locations, depth of bedrock, and other phenomena. Resistivity also has a direct impact on the corrosion in underground pipelines. A decrease in resistivity relates to an increase in corrosive activity. And most important for today's video, soil resistivity directly affects the design of grounding systems. Soil resistivity is the key factor that determines what the resistance of a grounding electrode will be, to what depth it must be driven in order to obtain low earth resistance, and even the type of grounding system that should be designed for this location. The resistivity of the soil varies throughout the world and changes seasonally. Soil resistivity is determined largely by the content of electrolytes consisting of moisture, minerals, and dissolved salts. A dry soil may have high resistivity if it contains no soluble salts. Let's take a look at a number of different soils and their relative resistivity. As the chart on the screen indicates, soils containing clay, cinders, or loam have a very low resistivity in comparison with sand, gravel, and stone. Moisture also significantly affects soil resistivity. Consider two samples of soil, a topsoil and a sandy loam. When completely dry, both are very good insulators with extremely high resistivity. However, when moisture is added to both samples, resistivity changes rapidly. Resistivity of the soil is also influenced by temperature. For example, this chart shows the resistivity of sandy loam containing 15% moisture with temperature changes from 20 degrees to minus 15 degrees Celsius. In this temperature range, the resistivity varies considerably. With these factors in mind, soil resistivity measurements are the key to determining the magnitude of effort that may be required in constructing an efficient grounding system. The simplest way to measure soil resistivity is known as the Wenner method. This involves placing 4 equally spaced and inline electrodes into the ground. The 2 outer electrodes, called the current electrodes, inject current into the soil. The 2 inner electrodes, called the potential electrodes, measure voltage, which is then used to calculate soil resistance. In our example, we have spaced the electrodes 10 feet apart and 6 inches deep. For this test, we are using the AEMC Model 6471, a 4-pole ground resistance tester. The 2 outer electrodes are connected to the instrument's outer terminals. The inner electrodes are connected to the inner terminals. Let's pause a moment to discuss how these terminals are labeled. According to international standards, the current terminals are called H and E. Some manufacturers label these terminals Z and X, while others use C1 and C2. Similarly, international standards define the potential terminals as S and ES. On some instruments, these are labeled Y and XV, and on others, P1 and P2. In this video, we will refer to the current terminals as Z and X, and the potential terminals XV and Y. The Model 6471 has the capability to automatically calculate and display soil resistivity, a value represented by the symbol ρ. To measure this value, turn the dial to the ρ setting and enter the distance between electrodes, as instructed by the instrument's user manual. Then press the Start button to take a measurement. After a few moments, the resistivity reading appears. If you regularly need to perform soil resistivity testing, consider purchasing an instrument such as the Model 6471 that automatically calculates this value. This will save time and eliminate potential math errors. If your instrument doesn't offer automatic soil resistivity calculation, simply take a resistance reading. For example, if you don't enter the electrode distance, the ρ setting on the Model 6471 displays soil resistance, which as you can see is 15.1 ohms. We can now use this value to manually calculate the resistivity of the soil. The complete formula for soil resistivity is shown on the screen. However, a more simplified formula can be used when the auxiliary electrodes are driven to a depth of approximately 1/20th of the electrode spacing distance, as we've done in our demonstration. In this formula, soil resistivity equals 2 pi multiplied by A, the distance between the electrodes in meters, multiplied by R, the reading obtained during measurement. So to calculate soil resistivity, we multiply 2 pi, or 6.28, by 3.05 meters, the metric equivalent of 10 feet. We then multiply this by our reading of 15.1 ohms to obtain a soil resistivity value of 289 ohm meters. A grounding system typically consists of a grounding conductor, a bonding connector, its grounding electrode, typically a rod or grid system, and the soil in contact with the electrode. An electrode can be thought of as being surrounded by concentric shells of earth or soil, all the same thickness, with each successive shell having a larger cross-sectional value over which the resistance is distributed. Note that increasing the diameter of the grounding electrode does not significantly reduce its resistance. For instance, doubling the diameter reduces the resistance by less than 10%. However, driving the ground rod deeper into the earth does substantially reduce the resistance. As a general rule, doubling the depth to which the rod is driven into the ground reduces its resistance by up to 40%. However, this has its practical limits. When a ground rod is installed, it's essential to test its resistance to ensure it is functioning effectively. The 3-point follow potential test is a commonly accepted method for measuring the resistance of single grounding rod or grid systems. The diagram shown on the screen illustrates the internal circuitry of a standard follow potential tester. Packaged inside a typical instrument are 2 independent circuits. One circuit is a constant current generator, the other a high-impedance voltmeter that measures the voltage drop and then calculates and displays resistance. By inserting auxiliary electrodes into the earth at certain distances from the electrode under test and then connecting them to the instrument, the operator sets up a bridge circuit within the earth. Current flows into the earth through auxiliary electrode Z and returns to its source through the rod under test. A voltage drop is developed between these points and is measured by the Y auxiliary electrode. By positioning the Y electrode at a number of different points between the rod under test and the Z electrode, measurements can be plotted and a characteristic curve becomes evident. In a full follow potential test, this involves taking a measurement at every 10% increment of the distance between the rod under test and Z. To ensure an accurate measurement, be sure to place the current electrode far enough from the ground rod under test so that the central measurements of the potential electrode will be outside the sphere of influence for both the ground rod and the current injecting electrode. The best way to determine whether or not the current injecting electrode is placed correctly is to perform a simplified type of follow potential test called a 62% test. This involves taking measurements at 52%, 62%, and 72% of the distance between the grounding rod and current injecting electrode. If the spheres of influence of the ground rod and current injecting electrode are in collision, readings taken at these points will vary considerably. When the ground rod and current injecting electrode are positioned correctly, readings will vary only slightly as measurements are made. To demonstrate, we will use the AEMC Model 3640 ground tester to perform a 62% test. Our test subject is an 8-foot ground rod. Before connecting the ground rod under test to the instrument, the rod must be disconnected and isolated from service. To measure our ground rod resistance, we connect the rod to the instrument's X terminal. We then place the current injecting electrode a minimum of 10 times the rod depth, or 80 feet, from the rod and connect it to the instrument's Z terminal. Finally, we place the potential measurement electrode at 62% of the distance from the rod to the current injecting electrode. Connect it to the Y terminal, and take a measurement. We complete the test by taking measurements at 52% and 72% of the distance between the ground rod and current injecting electrode. As we noted earlier in this video, grounding systems can be grids consisting of multiple rods connected together. Grids are commonly designed for substations and similar facilities to provide the lowest possible earth resistance values, as well as to create an equipotential zone throughout the entire station. The fence surrounding the substation is usually included in the zone for safety reasons. Multiple rod grids are typically constructed with ground rods exothermically welded to copper mesh, creating a large area of zero potential earth when installed properly. When performing a follow potential test on a grid system, we cannot use the depth of a single rod to calculate the placement of the auxiliary electrodes. Instead, the distance should be based on the maximum inside diagonal dimension of the grid. In addition to single rods and grid systems, other design grounding options are available. These include grounding plates. These are typically thin copper plates buried in direct contact with the earth. Grounding plates are often placed under poles or similar structures. There are also concrete encased systems, often called UFRs within the industry. These can be one or more copper rods, rebar, wire, or mesh encased in concrete, often incorporated as part of the building's foundation. Also used are chemical rods consisting of a hollow electrode filled with electrolytic salts. This option can provide an efficient ground system in locations where poor soil conditions are present, and spacing for electrodes is limited. Chemical rods are often used in conjunction with soil enhancement materials that improve grounding effectiveness. These materials can also be used in other grounding systems located in soils with poor conductivity. Follow potential testers are reliable and can be used in a number of different applications. However, there are some locations, such as where space is limited, access to the earth is unavailable, or the grounding system cannot be disconnected, where follow potential testing is difficult or impossible. In these situations, clamp-on ground resistance testing is fast becoming the alternative. Clamp-on testers offer the advantage of measuring ground resistance without disconnecting or de-energizing the system. These instruments also enable you to check both the resistance of a ground rod and its integrity to the rest of the system. To take a measurement, simply open the jaws, clamp onto the rod or the wire leading to the rod, and take a reading. The jaws of clamp-on instruments are designed with two independent shielded magnetic assemblies. One side is a transmitter that injects a test signal into the system at the ground rod under test. The other side acts as a detector that measures the resulting current that flows through the ground rod being inspected. This method provides accurate results similar to values obtained using the follow potential method. Clamp-on instruments can be used to measure the electrode resistance of pole grounds, pad-mounted transformer grounds, transmission tower grounds, and service entrance grounds, without the need for auxiliary electrodes. They can also measure true RMS neutral-to-earth leakage currents. Advanced clamp-on instruments, such as the AEMC models 6416 and 6417, also provide variable test frequency, loop resistance indication, ground voltage detection, and storage of measurements. The model 6417 also features Bluetooth wireless communication for connecting to a computer or phone apps. Note that AEMC Instruments manufactures a wide variety of products for measuring soil resistivity and grounding system resistance. Whatever your ground resistance testing needs, AEMC has an instrument that meets your requirements. If you'd like more information about ground testers or other AEMC products, please visit our website or call our technical assistance hotline. Let's take a moment to review a few of the major points we've covered. Grounding is a critical component of electrical systems because it helps protect equipment and users from electrical faults, lightning strikes, and other dangerous electrical anomalies. Grounding systems can range in complexity from a single rod driven into the ground to complex grids consisting of multiple rods connected with wire mesh, to other types of grounding systems incorporating plates, concrete, chemicals, and soil conductivity enhancers. Knowledge of local soil resistivity is essential for designing a grounding system appropriate for the site. The Wenner method is a simple and effective way of measuring soil resistivity. A follow potential test, for example the 62% test, is used for measuring the efficacy of a grounding system. In situations where performing a follow potential test is not feasible, clamp-on ground testers provide a good alternative. As we've seen, there are a number of different methods available for testing the resistance of grounding systems. Armed with proper understanding of the techniques and test results, ground resistance testing can be performed with ease. And be sure to check our YouTube channel for instructional videos on other topics in electronics, including the many products offered by AEMC.